Hello everyone, this video's topic is diamond silicon vacancy, and here I will give a presentation to introduce the paper Single Photon Switching and Entanglement of Solid-State Qubits in an Integrated Nanophotonic System, which is published in 2016. I hope my interpretation will help you to have a general understanding of the frontier work of this paper. Okay, let's get started. First, I want to explain why I chose this topic. We have well understanding of MV center after half semester's learning, and now we are familiar with the level structures and its application in quantum engineering. Although it has many advantages, as the paper said, but also some flaws are mentioned. I want to do a transverse study to see what are the common properties of this type of materials and in what else application can this structure in diamond be used. This paper is about the technologies and applications based on silicon vacancy center. What needs to be mentioned here is that from the perspective of research history, the research of the silicon vacancy center is more likely the continuation of MV center, because the MV center has been studied for nearly 70 years, but there are not many papers related to the silicon vacancy center, and most of them are published in recent years. Historically, it can be regarded as a branch of the research in diamond structure vacancy color center. The development of MV center has been relatively mature, so people can use its experience to further explore on the silicon vacancy center. Now, let's talk about the motivation and critical assessment of this paper. We need to know that an integrated platform of scalable quantum nanophotonics is very important for application in quantum science, such as quantum computing, quantum chips, and quantum communications. And efficient interfaces between photons and quantum emitters is the key for the integrated platform of scalable quantum nanophotonics. However, there are great challenges to realize such an integrated quantum platform in solid-state systems, and this work presented an architecture by integrating silicon vacancy center in diamond nanophotonic devices to overcome these challenges. What challenges need to be overcome? I think there is a big challenge in overall goal and some difficulties in implementation. The outstanding challenge is the weak interaction between single photons and individual quantum emitters in solid-state system. That means how to realize strong coupling between single photon and individual emitters for constructing an integrated quantum devices. And the difficulty includes how to suppress the effect of disjoint quantum decoherence of the coupled qubit systems, such as inhomogeneous distribution, rapid decoherence, and significant spectral diffusion in optical transitions. Also, the random positions of the quantum emitters in solid-state system, which makes the realization of scalable devices with multiple emitters difficult. Then we were curious about what are the advantages of the diamond integrated platform with silicon vacancy center comparing to competing technology. According to the paper, its advantages are very attractive. First, it is facilitated to realize the strong coupling between single photons and the silicon vacancy centers in diamond photonic crystal cavity. What's more, the positions of the silicon vacancy center can be precisely implanted into diamond waveguide or photonics crystal cavities. Also, the effect of inhomogeneous distribution, rapid decoherence, and significant spectral diffusion in optical transition can be greatly suppressed due to inversion symmetry of the silicon vacancy center, which result in the nearly lifetime broadened line-wise in optical transition spectra. Now we can go to the second part, technical assessment, including the main result and which technologies and methods are used in the experiments in this paper. The authors explain these results separately under each subtitles to show the method and technology details. The fabrication process and experiment involve lots of optics knowledge, which I learned in my undergraduate, and I know it's not wise to explain each concept and principle that are mentioned. I would try to simplify the details and focus on the main outlines. The first question is how they fabricate the diamond integrated platform with silicon vacancy centers. Here are the keys. Technique 1. The angle reactive ion etching is applied to fabricate the one-dimensional waveguide and photonic crystal cavities. Technique 2. The focused silicon ion beam implantation is applied to deterministically position at the center of each cavity for optimal coupling between an individual silicon vacancy center and the cavity mode. Technique 3. The annealing processing at 1200 Celsius degree in vacuum is utilized to form the silicon vacancy center and mitigate crystal damage. Figure 1 shows positioning and strong coupling of silicon vacancy center with diamond cavities. Next, what can the diamond integrated platform with silicon vacancy centers do? Here are some functions of it. The function 1 is that it has the ability to realize the quantum optical switch between the transmission and fluorescence emission at single photon level based on a single silicon vacancy center in diamond cavities. We can see they made an all-optical switch with memory by optically controlling the metastable orbital states of a single silicon vacancy in figure 2. The energy level structure and the preparation method of initial state is very similar to MV center. Use gate pause to choose state C or state U as the initial state. In the figure 2C and D, we can see that when state U is the initial state, the prop pulse will have high transmission rate and low fluorescence rate. If the initial state is state C, it's the opposite. So this is the switch. They also did an experiment to verify optical switching at the single photon level by using photon correlation measurement, as shown in figure 3. The key point is the value of G2, the second order correlation function in figure 2b. If we don't understand this function, it doesn't matter. We only need to know that it can be used to determine whether the scattered photons are single photon emission. In general, when this value is less than 0.5, we can assume that it is at single photon level. The result in this paper is 0.15, so it is a good result. Of course, the ideal single photon corresponds to G2 equals to 0. Function 2 is realization of tunable single photon source. It has the ability to implement the tunable single photon source by using Raman transition. Although in this system, the spectrum line-wise in optical transition was suppressed by some of the previous techniques, some uncertainties in the fabrication process still result in a relative broad bandwise of fluorescence spectrum. So how to solve this problem? The answer is to use Raman transition technique. From the figure 4b and figure 4c, we can see the virtual state that has a delta detuning from resonance frequency, which is the magical place of the Raman transition. The line-wise of Raman peak here is narrower than that of the fluorescence peak. Moreover, the Raman photon frequency and the spectrum line-wise can be controlled by controlling the Raman laser light intensity, which means the spectrally tunable single photons are realized by using Raman transition. And the function 3 is it has the ability to achieve the entanglement between two silicon vacancy centers in a diamond nanophotonic waveguide. Figure 5 shows such an entanglement by utilizing an efficient probabilistic entanglement generation scheme based on detection of indistinguishable photons from Raman scattering of two silicon vacancy centers. Figure 5D gives the second-order correlation functions from single silicon vacancy center and two silicon vacancy centers, in which the blue and the red lines respectively correspond to the classical mixture state and the entangled state of the two silicon vacancy centers after detection of a distinguishable photon. At last, what can we do to improve these technologies? The first thing is increasing the coherent time by operating at low temperatures or engineering the photonic density of states to suppress photon relaxation processes. The second is improving nanophotonic designs using slow light waveguides and cavities with higher Q ratios. Furthermore, the efficient fiber diamond waveguide coupling for improving the efficiency even exceeding 95%. For applications, first, their work shows possibilities for realizing large-scale systems involving multiple enders strongly interacting via photons. And because of the large cavity bedwise, more than 10 coupled enders can be addressed independently in a single cavity to form complex quantum nodes that efficiently couple to a fiber network. So such a system paved the way for the realization of integrated quantum networks with applications such as long-distance quantum communications. Okay, that's all. Thank you.